Hi. So now let's continue with the next method. So we just did the add element method. So we have the full method with the support method. I think. Private void add element. So that's done. It's saying uncheck cast. Should be okay. So now we'll do the remove methods. So one of them goes, actually, so we have remove element, that'll be fine, but remove min, I think they kind of switched it. You don't need to. I did a remove max, find min and find max. Those methods are mine, I created them myself. I didn't switch any nodes. So you'll see in a sec. So here we'll just do the public T remove element. So we'll just work under this one. We'll just do a little doc too, so we'll say removes the first element that matches a specified target element from the binary search tree and returns a reference to it. So here we'll say throws an element. You don't really not need to say this, but throws an element not found exception if the specified target element is not found in the binary search tree. So here we'll say param target element, the element being sought in the binary search tree. Then here we'll say at throws element not found exception if the target element is not found. We could have just put that bit about the element not found exception in this part instead of writing it twice, but that's fine. So here we'll just say public T remove element. So it returns a type T, takes parameter T target element, and here we'll throw the exception throws element not found exception. Here result points to null if is empty. Then we'll throw new element not found exception. So if is empty, throw a new element not found exception linked binary search tree. So if it's empty, we're trying to remove an element from an empty tree, then we're just going to throw element not found exception. We could have just thrown an empty, what was that one? Empty collection exception. We could have done that as well. Doesn't really matter. Either one works. Then we'll say here, we'll say else. We didn't really need to say else here, but that's the way the coder that coded this did it. This is from the textbook. So one of the authors. So we'll say a binary tree node of generic type T. parent. Maybe they come from a lot of languages too. I mean, like more than I know, so maybe they're used to it. It's just their style, that's okay. So binary tree, because we could have just said here, if it's empty, throw this, and it would have just started the exception propagation process. But then this wouldn't have been executed, so we wouldn't have had to say else. But I guess they just want to make it clear. The part that makes it difficult is that if we have a lot of code, then it's just going to get mixed up in more else statements, so it's a little confusing. So here, that's okay, we'll just say binary tree node of type T parent points to null. Then here we'll say, so 3 brackets, and then if comparable. So here we're going, they did it this way. I think we've done this before too. We've cast it every time we want to call the target element and want to compare. We could have just did a one cast and then just said target equals target element dot equals, but that's fine. It doesn't really matter which way you do it. Maybe they're just showing different ways to do it. Like intellij gives you the options to change it. We'll just say if comparable of type T target element dot equals root dot element. What's up here? Unchecked cast. It's okay, it's fine. You could suppress warnings if you want. So here we'll say here result points to root dot element. So it's saying, okay, if think about it, if we remove the root, we're going to have to shift some elements around, or else there's not going to be a root anymore. So I think the way they do it is they take the in order successor. That's the replacement method, so you might be jumping to that method in a sec. Do I have, because I don't have that exact definition here, so let me just take a look quickly. So this is, can't remember which one it'll be in, but we'll just try this one. So it's going to take the in order successor. So here we go, removing node from a binary search tree, or BST. So removing a node from a BST falls into 3 situations. So it's actually 4, because 1, the tree could be empty. And then, so the next, they said 3, so the node to be removed is a leaf, that's 1 situation. The node to be removed has 1 child, that's the second situation. And the third situation is the node to be removed has 2 children, so it's either a leaf, it has 1 child, or 2 children. Fourth one, it's empty, if you really want to consider that, which we already did up here. So if the node has 1 child, the deleted node is replaced by the child. So if the node has 1 child, so if we're deleting 5 and its left child is 4, then 4 will replace 5 and 5 will get set to null. So there's 2 ways to do it if the node has 2 children. An appropriate node is found to replace it. The children of the removed node becomes the children of the replacement node. So think about if you have a long linked set of data, like you could have millions of data, right, linked to this. So what's going to happen is you're going to have to link that whole subtree to the next subtree. Think about it that way. And the way they do it, or the way we're going to do it, is basically it's going to set that up all for you just by doing 1 shift. Is that you should be able to keep everything with just 1 shift. So if there are 2 options for picking the replacement node, so there's the in order successor, so that the node that contains the next highest value, and the in-order predecessor. I'm not exactly sure if predecessor is exactly the opposite of successor because they never explained how to do it that way. I'm pretty sure it's just it's okay. We can just do it the successor way anyways, if that way works. Or you can test different ways. Doesn't really matter. But here we're just going to you'll see. So we'll do a practice. We'll come back to the notes. We'll just try to remember. But if we take away 5, so if 5 has 2 children, let's say 5, we have a root 5, or we have a subtree 5, and its left child is 4 and its right child is 6. So if we delete 5, we're going to take the in-order successor, which means the node that contains the next highest value. That means we're gonna set the node, so we're gonna set the node to point to 6. So we're gonna shift 6 to take 5's place, right? So now 6 is the node and its left child will be 4, and we're gonna set 5 to null. We're gonna nullify it the same way as a linked list, basically. So we'll just do that. That's it. That's all it is. You just have to. I guess there's 2 ways to do it, but we're just going to take the next highest element and swap it for that. So just remember, in order successor, that just means take the next highest, the node that contains the next highest value. So we'll come back to that. So I hope that makes sense, and we will continue here. So remove element. So result points to root.element. And then here we're gonna call a method that we haven't created, and we'll probably shift to do that. So binary tree node of generic type t temp points to replacement, passing in root. So it's saying, okay, well, what's replacement? So replacement removes the element that matches the specified target element, the first element that matches the specified target element. So we'll just jump into doing this method because it won't really make sense if we just go with that. So here we'll say removes the first element that matches the specified target element from the binary search tree and returns a reference to it. Then we'll say throws an element not found exception. If the specified target element is not found in the binary search tree. Here we'll say at param target element, the element being sought in the binary search tree. At param node, the node from which to search. At param parent, the parent of the node from which to search. At throws element not, they've said it like 3 times, but that's okay. Element not found exception if the target element is not found. If the target element is not found. So here we'll just say private t remove element. We'll take a t target element, a binary tree node, binary tree node of generic type T, name node, a binary tree node of type T, parent, and then again we'll throw the exception, throws element not found exception. So let me just make that a little smaller, or that's fine. So here we'll just say T result points to null. If node points to null, throw a new element not found exception. So if node points to null, again we could have just thrown the empty collection exception. I think that might even be a mistake because if it's empty, it's not found, it's empty. But that's okay. So we'll just say linked binary search tree. Then they use else again. Then we're going to do a cast here, same thing. Actually, is this the? Oh, sorry. This is the second second support method. So where's this one? So, apologize for that. Just leave that. We're going to have to do that anyways in a sec. Just scroll down a little bit more to the method that we were, the replacement method. So we'll just go under here. We'll come back, and we'll say here returns a reference to a node that will replace the one specified for removal. So this is where our shift is going to come from. Our it's not really balancing. It's just a shift. It's just going to say, okay, we're going to take this node out and we're going to put another one in place for that node. So we'll return a reference to the node. Return a reference to a node that will replace the one specified for removal. So it's a little confusing, but all we're doing is just finding a node that's going to replace the one we're going to remove. In the case where the remove node has two children, the in order successor is used as its replacement. So we just talked about that. So hopefully that clears everything up. We're just looking for the next highest element. In order successor, we're just looking for the next highest element to replace the node that we're going to remove. So we'll say here at param node the node to be removed, and at return a reference to the replacing node. So here we'll just say private binary tree node of generic type T. We'll call replacement. Yeah, that's fine. Whoops, that's fine. So we'll say binary tree node of type T. We'll take a parameter node of type binary tree node of type T. Then here we'll set a binary tree node of type T. Result points to null. Then here we'll say if node.left points to null. So if node.left points to null and node.right points to null, which means that it has no nodes, it has no left child and no right child, then we'll say node.right points to null. So if node.left points to null and node.right points to null, then result will point to null. So we're going to replace it with null. It's just going to be null. That's all we're going to replace it with. Basically we're just setting it to null. But here if so there's going to be three options here.
it's going to be like node dot left is not equal to null and node dot right equals to null, and then the opposite of that, and then they're both two children there. So here we'll say else if node dot left is not equal to null and node dot right equals to null. So if one equals to null and one does not, so the left one doesn't equal to null, so there's a left child and no right child, then we'll say, okay, well, result points to node dot left. We're going to replace it with its only child. So if we're going to remove a node, we're going to remove, let's say we have 5, and we're trying to remove, let's just say we're trying to remove 5, and 5's only child is the 4. So what we're going to do, we're going to just take 4, remove 5, and put 4 in place of 5. We're going to shift 4 up, or it's going to become the root now, the subroot or whatever. You can call it subroot if you want. I think I did call it subroot at one point. That may help, but we'll just say result points to node dot left. So it's going to take, so if in the case of a binary search tree where you remove an element that has only one child, that child is going to become the element. It's going to now point to the place where the element was removed. So I hope that makes sense. So here we'll do the opposite of that. Else if node dot left points to null. So if the left child is null and node dot right does not equal to null, then we'll say, okay, result points to node dot right. Oops, did I put brackets there by accident? They didn't, so I won't. So we're saying, okay, if the left points to null and there is a right child, so let's say we have 5 for our root and its right child is 6, and we're going to remove 5. We're going to remove the subroot 5. Then we're saying, okay, we'll nullify 5 and then take 6 and point it to where 5 was. So 5 gets set to null and 6 gets shifted to where 5 was. So now 6 becomes a subroot. So now after those situations are done, so either both are null and we return null. It's this method is it's tricky, but this is the base of the removal here. This support method. This is where all the logic comes from. So if both are not null and one of them if there's only one child in the left, or if there's not only one child in the left and the right, then we'll say, okay, well, the last option is there's 2 children. So we'll say else here. Whoops. Else, what's happening there? Why is it automatically doing that? It's doing automatic stuff for me. Okay. Maybe too many brackets here. Okay, so else. Then we'll say the last option is binary tree node of type T. Current points to node dot right. So remember, we're gonna take the next highest element. I believe that's what it says. We're gonna take the node so the in order successor is the node that contains the next highest value, not the highest value in the tree, but the next highest value. So we're gonna say binary tree node current points to node dot right. Then here we'll say binary tree node of generic type T. Parent points to node. Then we'll say while current dot left is not equal to null.
So what we're doing here is we're saying, okay, current, take an object reference variable named current. We'll run through this as well. So we'll say take a binary tree node current, point it to the node that we're trying to remove to its right child, and it's saying while current, which points to the right node, then it's saying while that right node's left child is not equal to null, parent points to current and current points to current dot left, so it's going to traverse that left subtree till the last null element, till the very last leaf is going to get there, and it's going to be like, okay, well, parent points to the one above that and current points to current dot left, so the very last leaf, and the sub tree above it's going to be, its parent is going to be above. That's how you do that. We'll do an example of that later in the next method. So here we'll say current dot left points to node dot left. So current dot left points to node dot left. Current dot left points to node dot left. If node dot right does not equal to current, if the node dot right does not point to current, then parent dot left points to current dot right. Current dot right points to node dot right. Current dot right points to node dot right. Result points to current, and that's it. So don't worry about that. It might be a little bit hard to visualize. We're gonna do an example, and we'll do an example stepping through this to see what exactly is happening here without trying to visualize it. You probably get confused, so we'll come back, don't worry. That's about it. The next methods are pretty easy. Remove min, I do it myself. Like I did those ones myself. Not remove min. Remove max I did, and find min and find max. It works better than the way they did it. They also do a little shift. I don't know why. Because you're just supposed to remove the max. You don't need to shift anything. Because of course the min has no children and the max has no children, so they didn't need to switch anything. But that's okay. So we'll continue with what's that one? Remove not. Okay, so we'll come back to those. Replacement we just did. The last part. We'll run through that in the debugger, just to point out what's happening. So we come back to remove element where they called replacement, I think. So not this one. If you're following along in your IDE, we are back at remove element. So we're here, binary tree node 10 points to replacement, passing in root. So we'll say here, whoops, binary tree node 10 points to replacement root. So here we'll say if 10 points to null, and we'll set root to point to null. Then we'll say else root.element points to temp.element. Then we'll say root.set right to temp.right. Here we'll say root dot set left to temp dot left. Mod count plus plus, that is correct. Yeah, on a remove we're supposed to increment mod count, and on a add we're supposed to increment mod count as well, I believe. So else here we'll say where we mod count plus plus bracket and then else parent points to root if the three brackets or the three parentheses and then comparable of target element dot compare to root dot element is less than 0. Then result points to remove element, pass in target element. So this is for the support method. We'll do that in a sec. Root dot get left and pass in parent. Or we'll say here else result points to remove element, target element, and root dot get right, and parent as parameters. So if the target element dot compared to the root element, where are we? So this is our remove method. So here, if it's not null or if it's not empty, of course. So if the target element does not equal the root dot element, then we'll come down here to this bracket, then we'll say else. So if the target element, which is the element we're trying to remove, it does not equal the root dot element. So if the root is not the element we're trying to remove, then we'll say okay, well parent points to root if target element dot compare to root. So if the target element, so it's going to say okay, well we're trying to find this element, how do we find it? It's not the root, so what do we do now? So remember a binary search tree, the minimum values are on the left and the maximum values on the right. So it's saying okay, well is it less than or greater than the root? So let's say we have 5 and we're looking for 4. Then it's going to say okay, we're looking for 4. So is 4, which is a target element, dot compared to the root dot element, which is 5, is it less than 0? Well, is 4 dot compared to 5 less than 0? Is 4 less than 5? It is, that's true. So it's going to say okay, well result points to remove element, and then it's going to search the next subtree to the left. That's what's going to happen there. Same thing for the right if it's greater than. So if it's opposite of this, so let's say we're looking for 6, so target element 6 and the root is 5. So it's going to say okay, well if the target element, which is 6 dot compared to root dot element, which is 5, is less than 0, well is 6 less than 5? It's not, so that's false. So it's gonna hit this statement here. Result points to remove element. Then we're gonna hit that support method now. So the only confusion, I hope, is in the replacement method, hopefully, because in that last part that we said that we'll visualize that, because I didn't really get to explain it, that part, that well, but we're going to see it. We're going to watch the memory locations and the nodes and the links change. But if the the target element is the root element. So if let's say we're looking for 5, target element is 5, and that equals 5, the root element. We're going to say result points to root element. Then we're going to replace the root. We're going to replace the root with its in-order successor. Excuse me. So what's the in-order successor? So the in-order successor is the node that contains the next highest value. So that's going to be on the right of the root, the right child. So we're going to say, okay, temp point to replacement root. If temp is equal to null, so if there's no children, then return null. So this statement means, okay, we're looking for 5, we found 5. If 5 has no children, then return null. But if 5 does have children, then it's going to say, okay, well, root.element points to temp.element. Where's temp? So we'll figure out what temp is going to be. But basically it's just saying, okay, well, if temp is not null, that means if it has children, if 5 has children, then it's going to say, okay, well, root.element points to the temp.element, and that's going to be its in-order successor. So yeah, so this part's going to be like, okay, well, if 5 has 2 children, 4 and 6, then it's going to be like, okay, we're going to take 6, then it's going to set right to temp.getRight, which if it has children, then it's going to reset that node, and if the left has children, it's going to reset that node. So don't worry if you're having trouble understanding just from me trying to explain it. We will walk through these, at least these linked binary search tree methods, and we're going to be using at least the important linked binary tree methods. So now we'll come back to the remove element part, the support method, the one that takes a few parameters. So we'll say, okay, private t remove element takes target element, a node, a parent. We have t result points to null if node is equal to null. Throw a new element not found exception. So if comparable of target element dot equals node dot element, so if target element equals 2, so node's going to be this right here, the root.getLeft or the root.getRight. So it's only going to be either one of those. So it's saying, okay, if the target element equals to one of those nodes, or one of those elements in those nodes, then it's going to be like, okay, well, we found our target element. So it's going to say, here we're going to do a cast comparable of type t points to target element. Do I need a bracket there? Yeah. So here we'll put target element dot equals node dot element. Then open square brackets and we'll say result points to node dot element. So that node. Then we'll say binary tree node of type t temp points to replacement node. So it's going to be like, okay, find the replacement for the node that we found, the target element to remove, find the replacement for it. If parent dot right, so the parent is the right here, parent points to root, So if the parent that we're still carrying down from the above method here, we're carrying it down here. So it's saying, okay, if parent dot write points at temp, if parent dot write points to node, parent dot write points at temp, else, I need two equal signs here. So if parent dot write points to, or if parent dot write is equal to node, then parent dot write points to temp. Else parent dot left points to temp. So I promise you we're almost done. So it's been a 4. This has been the longest structure so far. I think it is the longest one in general. The heaps seems easier than this. Well, I think we do use these methods anyways. But we're almost at 4 hours now, and we'll still need some more time to test them and write a few more methods. So might be 5 hours. I might have to put that in 2 parts. So here we'll say parent dot left here. So else parent dot left points to temp. Then here we'll say mod count plus plus. So if the target element does not equal the node dot element that we passed into above, so it's not that first subtree, maybe it's a few levels down, which will probably be the case, unless we're just testing. But we'll say okay, else parent points to node if comparable of target element dot compare to node dot element is less than 0. So it's saying, okay, well, if it's not that node, the one that we passed in above for the target element, if it doesn't equal to the node dot element, this one right here, that line, if that's false, so if it's not the node in our subtree, then it's going to say, okay, parent points now to the node. Then it's going to say, okay, well, comparable target element compared to, so take target element, say we're searching for like 12 dot compared to, or say we're searching for 11 dot compared to node dot element. So the node dot element is going to be the next root, or the next subtree root basically. So it's going to be like, okay, well, is it, let's say the next subtree root 6, so it's going to be like, okay, is it less than, is 12 less than 6? No, that's false. So it's going to be like, okay, well, it's going to be on the right then because it's greater. That's all it's going to do. It's going to keep searching like that. So I hope you understand. If you don't worry, we'll still do the example. Here we'll call a recursive call. So we'll say target element node dot get left. Node dot get left. So here we'll pass in node dot get left as the next node and parent. Then here we'll say result else result points to remove element. So if it's not less than, then it's greater than or equal to. So remove element, we'll pass in target element. Node dot get right and parent. Then that's it, and here we'll say return result. So those are the last ones. Basically, we just have a few small ones left. Hopefully we don't have too many mistakes here. I can't even see it because the timer for the camera's in the way. That's the problem with writing them out like this.
sometimes you may get mixed up. Like here we have an error. I can't even see how many we have. So we have one there, add element, no dot left. What's wrong with that? Add element. Is that the support? No, it's not. That's just the normal method. Okay, so where are we here? If no dot get left. It is a support method. Okay, so it is in the support method. So we're saying if comparable element if no dot get left is equal to null, no dot set left to binary tree node, else add element, no dot get left, no dot left dot get left. Okay. Hopefully we don't have too many errors like that. So this one itself is 206 lines so far, with spaces in between some of them. The other one was like 500-600, right? But most of these are just one-liners, but still it's a lot. Once you get up to 1,000, it's considered a long code. Not that long though, obviously there's code with like hundreds of thousands of lines, but that's okay. Oh, what's wrong with this? The format is wrong. Okay, so binary tree node replacement. I'll probably come back and fix these after. Well, okay, so if no dot left is not equal to null, and no dot right is not equal to null. Okay, there's two brackets, supposed to be two brackets here. Done. So we probably will have to do a bunch of those, because obviously I've typed this out pretty quick. Within, you know, like 4 hours, but still. So we'll come back. Here we'll do remove all occurrences, just a small one. So we'll go under that. It's not really even showing the method. There's no IntelliSense going on. Okay, there it is finally. So here we'll say removes elements that match the specified target element from the binary search tree. So at param, at param target element, and here we'll say throws element not found exception. So some of the same stuff I'm just going to type it. I won't repeat it because we've done it like 20 times by now. So here we'll do public void remove all occurrences. Maybe with the E. Remove all occurrences. So we'll say takes a target element as parameter.
and throws the exception, element not found. Throws element not found exception. Here we'll call remove element, pass in target element. So remove all occurrences means it's going to remove every occurrence of the element. So if we were trying to remove 5, and we have 5 20 times, it's going to remove all of the 5s. So we do that with a loop. So they use a try, you don't need to use a try. But we'll say here while contains, do we do that? Cast it to T. While contains T bracket target element bracket again. Remove element target element. So that's our try. Here we'll have a catch. They just did it with an exception. Element not found. Exception. No, and they didn't put anything inside the brackets. A little bit strange, but that's okay. It works, I guess. So here we have the last 4 methods, which are really simple. So we have remove min, remove max, find min, and find max. And that's it, we're finally done. So, remove min, they do a swap. You don't need to worry about it, but you'll see what I mean. So they remove the min, of course, with the logic that you should know to find the min and find the max. It's a traversal down one side of the tree. Excuse me, so it traverses down from one element, it keeps finding the next lowest element. We do that with a while loop and 2 object reference variables. And then after we do the max, which is the same thing, just to the right, of course, to find the max. To remove them, they shifted an element for no reason. You don't need to do anything. All it says is remove the max. It doesn't say shift anything. You don't need to because it's just a leaf. But so to find min, we just need 1 object reference variable. We do the same thing. It's just easier than remove. It's easier than remove because we just need 1 object reference variable, but otherwise it's exactly the same. So think about it, when you remove something, you locate it first, then remove it. When you want to just find the min, you just need to locate it, you don't need to remove it, so it's easier. So here we'll just say removes the node with the least value from the binary search tree and returns a reference to its element. Throws an empty collection exception if the tree is empty. Return a reference to the node with the least value. Throws empty collection exception if the tree is empty. So I'm just gonna grab some water real quick. Try not to spill it on all these wires I got going on. For the mic and the mouse and all that stuff, the keyboard. And I got my laptop here too. Alright. So it throws empty collection exception if the tree is empty. And we'll call it public T remove min. We'll throw empty collection exception. So here we'll say public T. Oops, sorry, the mic foam was falling off. So we'll say public T remove min throws empty collection exception, empty collection exception we'll say T result points to null. If is empty, throw the exception. Pass in the string. So we'll say else. You don't need an else, but what they did else. So else, and then if root dot left is equal to null. Result points to root dot element. So we're saying, okay, find the min, and the root's left child, which would be the next minimum value, is null. Then, well, what's the next minimum value? If that one's null, then it's going to be the root, not the right child, because it'll be bigger than that value, than the root value. But if root's null, then we have this, throw the exception. So if root dot left child is equal to null, then result points to root dot element. Root points to. So if the root's the minimum, then we'll say, okay, we're going to take the in order successor. So then root points to root dot right child. That's it. Then we'll say else here. Binary tree node of generic type T. Parent points to root. Or they did it a little different than I did. That's fine. We'll go over both ways. Personally, I think mine's easier. So then here we'll say current points to root dot left. Parent points to root. Then they say current points to root dot left. So here we'll say while current dot left. So it's like while head dot next is not equal to null. What we're saying here, while current dot left is not equal to null, then parent points to current. So it's going to say, okay, we'll take an object reference to that pointer before you shift, because we're going to need that one later. Then we'll say, okay, then shift to the next element, then traverse to the next element. So, or the next node. So then current is set to current dot left, because we're going to the left, and then to the next left, and then to the next left child, because we're searching for the minimum value. So here we'll say result points to current dot element. Parent dot left points to current dot right. Mod count plus plus. Whoops, return result. That's it. So that's the way they did it, and I'll show you the way I did it. So the last three methods I did completely from scratch. I don't even have any doc for them. So public T remove min should be correct. T result points to null. It's empty, throw. Else if root dot left is equal to null, result points to root dot element. Root points to root dot right. Hopefully we didn't mess anything up along the way. So binary tree node of generic type T parent points to root. Binary tree node of type T current points to root.left. While current.left is not equal to null, parent points to current points to current.left. Result points to current.element, parent.left points to current.right, mod count plus plus, return result. Should be good. So here I have a public T remove max. I did it a little differently. So throw the exception. If it's empty, throw the exception. Pass in the string for the type of the collection. Then here we'll set T result, just an empty object reference, and we'll say here root.getRight. So if root.getRight is equal to null, so we're trying to find the max. So if the root.getRight is equal to null, then same logic here, result points to root.getElement. Root points to root.getLeft because there's no other values. So if we're moving the root and there's no right child and we're looking for the max, then the max is going to be the root. And if we remove the root, then there's going to be no other value, so we're going to say, okay, take the left child then to be the root. So root points to root.getLeft. So I was going to say, okay, well, if the root.getRight does not equal to null, meaning it has values, there is a subtree, and we'll say, okay, create an object reference variable here. So binary tree node of type T temp points to root. Then here we'll say binary tree. This is where I changed it. So binary tree node of type T parent points to temp. So they did something different. They said parent point. I said parent points. Sorry, they said parent points to root. I did that. I said temp points to root. So whoops, no, I didn't. Yeah, see, I switched it. I said temp points to root and parent points to temp because parent is above temp. They did it differently. They said, okay, well, parent points to root and current points to root.left. So it's a little different. Personally, I find my way easier because it does it itself. Like when it iterates, it just sets it each time. So here we'll say parent points to temp, right? So we make sure it's pointing to the parent node, to temp's parent, before we change temp to point to temp dot get the next node. So at this point, parent's still pointing to temp, and temp's now pointing to the next child. So here, then we'll say result points to temp dot get element. Oh, and I added some stuff here too, so I nullified it. So I said, okay, well, temp, set your element to null to ensure we set up everything for garbage collections. So then we'll say here parent dot set right here to null. I don't think they did that. They just left the values on the side. So it's good to know this too. Then we'll say temp points to null to really get rid of the object reference variable at the end that we use as pointers. Then we'll mod count plus plus. And then we'll set, oh, we'll say return result. Is that getting underlines for that? Why is that? Did I forget an else? It should have been, yeah, we did forget an else.
So if root dot get right points to null, result points to root dot element, root points to root dot get left. And we should have said else here. Apologize for that. So just else. Where does that go? That goes with this. That's all messed up now. So we'll shift those over. What's this? Whoops, did I forget the while too? I apologize. So here, okay, let's just go back from the beginning. So if root dot get right is equal to null, result points to root dot get element, root points to root dot get left, else binary tree node of type T points to root, parent points to temp, then here we need a while, so while temp dot get right does not equal to null. That's going to say okay. These are backwards. That's fine. Then here we'll say okay. That stuff. Where is that going? There we go. Should be right. So else, close the else after 10 points and null, then under that, mod count plus plus. Done. Remove min and remove max are done. Hopefully they're correct. And we just have two more. Small ones. So it's exactly the same logic, we just don't need to nullify anything. Don't swap anything, and we don't need to create two object reference variables. So you can go ahead and create those on your own. I'll see you guys next time. No, I'm just joking. So here we'll just write down. Well, I feel like I'm missing it. Okay, no, where's our final bracket? I think we're missing one. Yeah, we are. There we go, public class. So this should be over here. So find min now. So public T, find min. Throws empty collection exception. Empty collection exception. Throw the exception if it's empty. Throw new empty collection exception. Linked binary search tree to result if root dot get left is equal to null. Result points to root dot get element. No shifts again because we're just finding. Else binary tree node type T, 10 points to root, while temp dot get left is not equal to null. 10 points to temp dot get left. We don't need to create a parent node. Result points to temp dot get element. Temp points to null. Return result. I think that's it. So you can see the logic here. It's similar, just less steps. It's easier. Tiers also throw. Whoops. Forgot a bracket here. What?
if is empty, throw that, then t result. If root.getLeft points to null, result points to root.getElement, else object reference while temp.getLeft is not equal to null. Temp points to temp.getLeft, result points to temp.getElement, temp points to null. So we did nullify the temp. Return result. So this one seems easier than these ones. Maybe because I created them, I know what's happening. Maybe you'll find that too. Your own code is much easier to understand than someone else's. And then find max, it's literally just the same thing. It's just we just change right. So I'll just type it out. What's happening here? Excuse me, I think we got an extra bracket. What's this? If, else, while. So why is the bracket here? That's fine, should be fine. Alright, so public t find max throws empty collection exception. It's a question for you: is C going out of topic for you? I mean, do you think C programming is going extinct? You can let me know in the comments what you think, because I guess Apple iOS is they're trying to switch over to Swift completely and get rid of C. So it seems like C is going to be completely extinct then, because it really, like, it won't have any use for Apple, so it'll just have use for maybe like some Microsoft stuff. But they usually mostly use C# and C++. So maybe just for some system stuff. I'm not, because obviously Apple really brought it popular, really made it popular. But anyways, we'll talk about that next time. So if is empty, we'll say it's kind of silly that they're doing that as well. But anyways, we'll say throw a new empty collection exception. But on that note, honestly, I think all those languages, maybe even probably even Java for Android, in the next 5 years they'll probably go extinct too, because even Swift will go extinct, because I think everyone's going to be using the multi-platform languages like React, JavaScript, React Native. I think they have Xamarin and Flutter. And I think out of all those, React is the most popular. Flutter is brand new. Xamarin's kind of old. It's based on C#. No one really uses it. So mostly React Native is the place to be right now. And you can create web apps and an app for Android and Apple just with one code. So you don't need to create like 3 codes, one for Android, one for Apple, or excuse me, one for iOS and one for a web app. So you just need to write one code, you can deploy it on all 3 applications. And that came out of maybe within the last few years. That really got popular at least. So now that's the thing. So I feel like unless Java becomes like that, then there's nothing. If Oracle does that, then there's not really going to be anything out there, because C is already going extinct. But anyways, we'll just say t result here. We'll say if root.getRight. By the way, we'll be doing a JavaScript series, a few series down the road. So if root.getRight is equal to null, result points to root.getElement. Then we'll say else binary tree node of generic type T, temp points to root, while temp.getRight. I think we still will be doing a little bit of C using Linux. We're working with Linux stuff, so that'll be coming up after Android. So while temp.getWrite is not equal to null, temp points to temp.getWrite. Temp points to temp.getWrite. This series is almost over anyways. Just maybe 3 more data structures. So result points to temp.getElement. Temp points to null, and then result points to return result. So it should be exactly the same I was talking, but I'll just double check. T result. So throw the exception if it's empty. T result. Empty object reference variable points to null at this time. If root.getWrite is equal to null, result points to root.getElement. Else binary tree node of generic type T temp points to root, while temp.getWrite does not equal to null. Temp points to temp.getWrite. Result points to temp.getElement. While temp.getWrite does not equal to null. Temp points to temp.getWrite. So it's going to keep iterating till it. While temp.getWrite does not equal to null. Or looping, I should say. Then result points to temp.getElement. Temp points to null to nullify. Return result. That should be it. It is getting a little late here, so I'm going to pause the video, and we will do the test for these methods and these methods in the following section. So I'll see you guys there. Thanks.